In block-to-block transmission, data and signals travel together as packets. Hence, similar and different type of information has to be packaged together. In Verilog, it is very explicit, clumsy, and error-prone. So, typedef, structure, union, and enumerated data types have been borrowed programming languages. Address, data, and control bits can be packed together using structure. Same memory location can be used for 32-bit word or 216-bit half words or 4 bytes with the help of union. Bit sequences corresponding to read, write, and reset can be mapped like a lookup table using enum or enumerated data types. Thus, all these borrowed data type gives better ways to organize, reuse, and manage complex packet transactions. So, stay tuned, stay focused. Hey guys, welcome back. In today's episode, we will be discussing the below points. Overall, we will talk about why int, typedef, struct, union, enum, all these concepts are imported from programming languages into SV. Next, we will go in detail of the int, that is a strongly typed integer in SystemVerilog, its role and advantages. Next, we will talk about the typedef, that is simply reusable type definitions, its syntax and advantages in SystemVerilog. Next, we will talk about struct, a group-related data, that is a structured data, its syntax and advantages in SystemVerilog. Next, we will go on union, the shared storage for different data types. We will talk about the syntax and advantages in SystemVerilog. Finally, we will embark on enum, simplify state machine and control logic. Here we will talk about the syntax and advantages in SystemVerilog. So in today's episode, we will be discussing all of them with example. Why the int, typedef, struct, union, enum, all these concepts are imported from programming languages into SystemVerilog. These were not there in Verilog. These are available in SystemVerilog. SystemVerilog is a hardware description language, but it borrows heavily from the software programming languages. Why? Because as chips grow more complex, we need better ways to organize, reuse, and manage information just like programmers do when they write large applications. Concepts like int, typedef, struct, union, enum were imported directly from programming languages to give us more expressive power. These are not just fancy keywords. They help hardware designers think in terms of data types, grouped information, code readability, and maintainability. So instead of thinking just in terms of bit 31 down to 0, A, B, C, etc., we now describe rich behavior and data structures that better represent real-world systems, whether it is a packet header, a memory map, or a protocol command. In SystemVerilog, we deal a lot with complexities, lot of protocols, etc. Now, let's dive in and explore how each of these elements help us in design hardware that's not only functional but clean, scalable, and reusable. Let us move on to the next slide. Int, a strongly typed integer. Ever get tired of typing logic 31 down to 0 over and over again in the code, or worse, making a small typo in long signal declaration that breaks your entire design? Now let us see about the int. The int type from programming languages provide 32-bit signed integer in SystemVerilog, making it easy to perform arithmetic operations and represent numerical data. It is easier to use compared to traditional Verilog, range, or where, which were ambiguous for arithmetic. That means sometime we need to do some arithmetic also. Now let us see the example. Here we have a module int example, and inside that we have int a10 signed 32-bit integer, int b-5, int sum. Now in the initial block we do the mathematics. So initial, then begin, then sum equal to a plus b, and we display the sum here with the $display command, and we end, and here we end the module. So this is very simple. The use of integer helps to allow mathematical operation inside a HDVL, that is hardware description and verification language. Now let us move on to the next slide. Typedef. Just like in programming, SystemVerilog gives us a smarter way, typedef. It lets you to give a name to a complex or commonly used type, like creating a nickname for a long phrase. This is especially powerful when you are working with large buses, custom data types, or need to make your design easier to read and maintain. Let's see how a simple alias like word_t can help clean up your code and keep things consistent. Typedef allows naming complex data types, making code modular, reusable, and easy to maintain. We are defining a type using the typedef. That is true for the programming language and true for the SystemVerilog. It reduces the redundancy in code where the same type is used repeatedly. And that is the case because when we have a large system design, there we have to use the same data type over and over again in multiple modules for various purposes. Now let us see the example. So here we type the typedef, that is the keyword defined. We write logic 31 down to 0 is a bus and we name it as word_t. So this creates an alias for the 32-bit logic. Now in module typedef example, we have word t, that is data. So we instantiate this type of data in this variable. Now in the initial block, we use data and we give a hex representation here and we print it using the $display command, that is data %h then data. So it outputs the data this, and here we end the module. So you can see that we can make a shorthand of a complex data type into a single nomenclature using the typedef. So now instead of repeating logic 31 down to 0 across 20 modules, you define it as word_t and use it everywhere. This isn't just about saving keystrokes, it's about building a code that is modular, maintainable, adaptable. If you ever decide to change the width to 64, change it in one place and it will be rippled down all the places and you are done. With typedef, you not just writing HDL, you are shaping a scalable and professional design environment. We are done here with this particular slide, so let's move on to the next slide. Struct, the group related data. Also it is referred as structure. In digital design, often we deal with relative data like a packet that has an address, some data and a control bit. But in Verilog, we typically declare each of these separately, which we can get messy fast. SystemVerilog gives us better way, the struct. Just like in programming, a struct, that is a structure, lets us group related variables into a single unit, like putting them into a labeled box. Whether you are modeling a data packet or a memory transaction or a bus response, the struct make your code more organized and easier to understand. Let's look at a simple example how grouping fields into a packet T structure. Packet T is here our structure, improves both readability and maintainability. So the struct or the structure is used to combine multiple variables into a single unit, reflecting hardware packets or complex data structures. It simplifies data handling and improves readability, especially test benches. Now let us see an example. Here we have typedef, then struct, and here at the last we have its name, that is packet_t. And what does it contain? It contains address, it contains data, and it contains valid or invalid. And here we can see it is of different width and it is a single where-like structure and it's defined with logic, which is better than the razor where. Next we define the module, the struct example. Here we have already defined the packet T and here we are using the packet_t is as packet. So we have the initial block. Here we type the packet.address is this hex data, packet.data is this hex data, and packet.valid is this data. Now looking at this initiations of the data, you can recall that in Python also we have this dot operator. It's more like a object oriented thing. So you can assume that the object is there, it is defined in its class and it is instantiated. Similarly here we are using this. And next we have the display, which is similar to printf command, and here we do the %h, %b for address, data and valid. And here we give the packet.address, packet.data and packet.valid. So this way we can assign the values and we can print the values, and here we get the output like this, and here we end the module here. So looking at this example, now you are able to combine multiple things into one particular packet, and typically this packets represents the packet exchange exchange through different protocols in the LSI design. There obviously you will have various kinds of data that are packaged together and sent together in real hardware, and that we represent here with the struct, that is the structure. By using struct, you have just reduced 3 separate signals into one clean logic unit, and your intent becomes crystal clear. This isn't just about saving the space, it's about writing test benches and RTL that are modular, easier to debug, and ready to scale with complexity. However, in a contradiction, it might seem to you define this as complex, but it actually in turn in a large design reduce the complexity and help you. As your project grows, especially when modeling protocols or handling transactions, struct become your go-to tool for clean and smart data representation. So here we are done with the struct. Let us move on to the next slide. Union. The union is shared storage for different data types. Imagine you are working with the same set of bits, but sometimes you need to treat them as full word, sometimes as 2 halves, or other times as individual bytes. That means either it could be used in a packaged manner or a segmented version of it. In Verilog, you would have to manually split and reassign the values, which is error-prone and tedious. SystemVerilog offers a smarter solution, the union. It lets multiple views of data share the same physical space. It's like having one drawer and labeling it differently depending on what you need. The contents could be socks, shirts, or accessories as your choice. Now let's see a practical example where a 32-bit word can be accessed in 2 half words or 4 bytes, all from the same memory location using union. So union allows multiple data types to share the same memory location, making it efficient for hardware structures like multiplexer or overlaid registers. And here is the example. Here we write typedef and then union, and here we give the type name at the last. And what contains within? All of them are logic. 31 down to 0 is the full word. 15 down to 0 is half words of 2, that is half of the full word, and we have logic 7 down to 0 byte, and here we have 4. This gives access to 4-bit bytes, this gives access to 16-bit words, and this gives access to full 32-bit word. So this way we define a union. That means the data is same. However, we can have different slice of it. Next, we define a module with union example, and here we use data underscore u, which is defined here, and instantiate with data. So we write data full word is this hex data, set the entire 32-bit data here, and with the printf like command, that is $display, we can print the half word in 2 halves. Okay, that is the data.halfword 0 here and data.halfword 1 here. Okay, so you can see the output will come as 2 halves, this and this, and we use again the $display like a printf structure, and here we print byte, 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 that means 4 bytes, and here we give the data byte 0, data byte 1, data byte 2, and data byte 3, and as a result we get EF, BE, AD, and DE, the 4 bytes. So you can see that when we have a union like data type, we define the full 32-bit word, and inside that we have multiple slices. Now this might contain instruction and data together, and we can split it as per our need, and that's why we need this kind of data structure in SystemVerilog. With just one declaration, you have unlocked 3 ways to view the same data, full word, halves, and bytes, without duplicating the storage. That means the same storage, but we take out the slice we need. This kind of flexibility is incredibly useful in hardware design, especially for building multiplexers, decoders, or register maps where bit level control matters. So next time you need multiple interpretations of the same signal space, think of union. It's not just efficient, it's elegant. We are done with this particular slide. Let's move on to the next slide. Enum. Simplify the state machine and control logic. Now let me tell you what does the word enum means. Enumerated data types. And this is not introduced in SystemVerilog, it is borrowed from the programming languages. In case you have came across in this C, you can recall your details from the C language. Have you ever looked at the state machine code and wondered why 2-tick B10 really meant was that the right or maybe reset. When everything is hard-coded in the binary values, it is easy to get lost and even easier to make mistakes. SystemVerilog gives us enum, a way to name each state or constant with a meaningful label, just like red, yellow, green, instead of 1, 0, etc. With enums, your code becomes readable, safer, and much easier to debug. Let's see how a simple enum example can clean up your state logic. So enum that provides a clean, readable way of defining names for states and constant, reducing errors associated with hard-coded values. It enhances debugging and human-readable state names instead of numerical values. Now let us see the example here. So here we give the typedef command, and here we define enum, and it is logic 1 down to 0, and we give a name for this, that is state underscore t, and inside this we define idle is 2tick b00, read as 2tick b01, and write 2tick b10. So we define the exact binary combination inside this enumerated data type. Instead, every time you go and see and check and define the values, we have a shorthand here. Now further going into the example, we have the module and enum example here, and as we have defined state t here, we are instantiating it as state t with the current state, and we can have a next state also. So the current state is idle. Okay, so the idle code, this will be picked up, right? So in $display we give the percentages, and then we give current state dot name is the idle. Then current state is read, and we can again print it, right, using the $display command and percentage case, and we get the current state name, and here it is read. We can change it to write. So this way we can have different set of data sets named as per our need. And you can recall in C language we had a macro system hash define like that, but that was very limited capability, but this has a very wide flexibility. So each and every sector of the design we can have a different enum that represent its own states. Okay, so instead of memorizing the 2tick b01 for read, you have just write read, and when you debugging you see the state names not confusing numbers, because humans are not ready for 1zip. That is for the machines, that is for the logics. For humans we need text, and here we have it. This not only reduces bugs but also improves collaboration. Anyone reading your code, even for the first time, will understand what each state does. As your state machine get more complex, enum becomes an essential tool for writing clean, scalable, and error-resistant control logic. So that's how you have the control over the mistakes. Initially, it might appear as a very complex thing to define, but in the usage perspective, this will make it very simple. The code, the debug, everything. So we are done here with the presentation of today's episode. Thank you very much for watching up to this point, and don't forget to like, share, and subscribe. In case you have some dislikes, put that as in words in the comment section down below. And bye for today.